All right, we're going to finish out this section by looking at the derivatives of logs and exponential functions that have bases other than e, and to see what happens. Now, we'll do the log first because I think that's a little bit easier, because remember the change of base formula for your logs. Log base b of x, you can change it to any other base, log base a of x, as long as you divide by log base a of the old base. That it's basically a scaling, that every log is nothing more than a scaling factor of each other. So pretty much if we want to convert to base e, usually that's the one that we're most concerned with, log base b of x is natural log of x over natural log of b. So this is what we're going to utilize in order to find the derivative of log base b of x and see what happens. Because right now we only know how to do the derivative of natural log of x. All right, so we want to find the derivative of log base b of x with respect to x. So we're basically going to take the derivative of the natural log of x over the natural log of b. And what we want to remember is that in this problem, what we're basically doing is the derivative with respect to x. This is 1 over natural log of b times natural log of x. Now I'm splitting it like that because this is not a quotient rule problem. Natural log of this base that you know, this is a constant. So when I have a constant here, the derivative of a constant times a function is the constant times the derivative of the function. And the derivative of natural log of x is 1 over x. So it becomes 1 over natural log of b times 1 over x. So pretty much the derivative of any log, it still has this 1 over x, but it has this additional scaling factor that you will need to add in. So for example, let's see how this is used. Okay, so our final kind of rule that you're going to memorize is the derivative of log base b of x with respect to x is 1 over natural log of b times 1 over x. And then just like before, this is also only true where x is greater than 0 because of the domain restriction over here, that if x is less than 0, then it's non-existent because this function's not differentiable for x less than or equal to 0. All right, so we want to find this derivative, and again, just jumping right in, we have a chain rule problem. So I want to find the derivative. My u is 5 minus x to the 4th. So I'm going to do the derivative of log base 3 of u, which is going to give me 1 over natural log of 3, right, times the derivative of the log, 1 over u, right, because this is a u, 5 minus x to the 4th, times the derivative of the u, which was going to be negative 4x cubed. So I kind of cheated there. I kind of jumped right from this to a chain rule problem, that the derivative of log base b of u with respect to x is going to be 1 over natural log of b times 1 over x times du dx, or u prime. Oops, sorry, not 1 over x. It should be 1 over u times du dx, or u prime over u. U prime over u. I kind of like to do it as 1 over natural log of the base, 1 over u, u prime, or du dx in my version when I do it. Okay, so here are your two rules, log base b of x and log base b of u. And again, my preference is to do it this way because I don't like to forget the u prime. So I do 1 over u times du dx. So that way I kind of don't forget that part. All right, so that's that. That's our natural log and our log base b. Now, I'm going to let you do the 2 to the x and graph your derivative using, well, now let's go ahead and do it. This real quick. Get it out of the way and be done with these notes. So we're going to graph 2 to the x here. Oops, clear. 2 raised to the x. All right, and I hate it in this new calculator because I never figure out what's where. So let's delete 2 to the x. And then my derivative, just to kind of see what I have. So I'm going to clear that out because we don't need that. So let's just take a look at the graph. So here's my 2 to the x exponential growth. Now remember, e to the x was its own derivative. But what we see here is when our derivative starts coming in, we're like, oh yeah, it looks like it's about the same. Is it going to be the same? Well, then you start to see, oh, it's starting to be off a little bit. So, oh, there's a little bit of a scaling factor on this one as well. Just like the log, the change of base is going to give us a scaling factor, that we're not going to quite get what we had, that the rate of change is going to be a little bit different than what it was. And it's going to have a scaling factor. So what we're doing here is that, and I'll leave you to do phi to the x, is that the derivative of 2 to the x with respect to the x is a vertical scale of 2 to the x. So it's not exactly, the derivative is not 2 to the x, it's a scale of 2 to the x, a constant times 2 to the x. And so the idea is we need to figure out a derivative. Now what we're using here is that if I have b to the x, this is your change of base for your exponential functions. I want it to be a base b, and wouldn't you agree that this is true since b equals e to the natural log of b? Because these are inverses, e and natural log would cancel out, and b equals b. And so what I'm doing is I'm using the change of base to change from a base b to a base e. All right? So I want to find the derivative for b to the x. What I'm going to do to find the derivative of b to the x with respect to x is I'm going to employ the change of base formula. I'm going to take the derivative of e to the ln of b times x with respect to x. And remember, this is a chain rule problem now. So for me to take the derivative of e to the u is e to the u times the derivative of the u, and that's a constant times x, so its derivative is simply ln of b, the constant. So what we've basically shown here, because now I'm going to simplify this back out, I only put it in just to figure out a way to use the e to the x or e to the u to do the derivative. E to the ln of b is just b to the x times natural log of b. So our general rule that we're going to be using for this is that the derivative of b to the x with respect to x ends up having a rule that is natural log of b times b to the x. That you have a constant scaling factor in front, just like you did for your logs. All right, so here's our rule. And for some reason, simply because I like to have it, I like to write it afterward, and that's usually the way that we do this. B to the x, the derivative of exponential is itself times the scaling factor. And then if it's b to the u, and you're trying to take the derivative with respect to x, then you want to do your b to the u itself, the scaling factor, ln of b, times your du dx, or your derivative of your u. And also kind of another point to look at is when you're looking at your derivatives of the logs and the exponential functions, that the derivatives happen to sort of be inverses of each other or reciprocals of each other, and that will come into play, but we'll talk about that more later. Let's do a few of examples. At what point on the graph does this function have a tangent line that has a slope of 2? All right, well, first thing I need to do is the tangent line slope is dy dx. So I want to find the derivative. The derivative of 2 to the t would be 2 to the t times the natural log of 2. Oh, I'm not taking the derivative. I'm taking the derivative with respect to t here. Okay, so that's my variable. So 2 to the t, and then the constant goes away. And I want to know, when does that derivative have a slope of 2? So now we're going to solve. 2 to the t equals 2 divided by natural log of 2. And then how to solve this exponential equation, I'm going to take the log of both sides. So the natural log of 2 to the t equals the natural log of 2 over natural log of 2. And this would cancel on this side. And so we end up with t equals the natural log of 2 over the natural log of 2. Doesn't matter that that's ugly looking. I mean, it's just a number. But they wanted to know at what point this has. All right, at what point? That's only the t, so I need to come back in here and go, all right, the x-coordinate would be this. And now I need to find the y-coordinate. And the y-coordinate, remember, you plug in, all right? And so I'm basically going to plug in 2 to the natural log of 2 over natural log of 2 minus 3. And the good thing about the FRQs and things like that, you don't need to simplify, so I can leave it there. All right, now the other thing is kind of looking at some of these items and when we're looking at things like this, we don't always want to just plug and chug and use the derivatives. We want to remember our log properties because simplifying is always good. So the first thing that I'm going to do for this, I'm not going to take the derivative at the beginning. I'm going to simplify. The 2 can move inside. This can become e to the natural log of x squared. And then that allows me to use the inverse property, which means that really all I'm doing is taking the derivative with respect to x of x squared. Oh, isn't that nice? That derivative is 2x. That if we simplify early and often, that will help us when we're finding our derivatives. Same thing is true here. I'm going to recognize that log base a of a to a power, that these are inverses of each other, and so they cancel out. So I'm really just taking the derivative with respect to x of sine of x, and the derivative of sine is cosine of x. So don't make something a chain rule problem if you don't have to. Even here in C, 8 is a power of 2. I can rewrite this as log base 2 of 2 cubed to the x minus 5. And then if I do that, I can do a little bit of algebra 2 simplification. This is, you multiply your exponents here, so I would have log base 2 of 2 to the 3x minus 15. And then the log base 2 and exponential 2 will cancel, so I'm really taking the derivative with respect to x of 3x minus 15. So my final answer is 3. So simplify early and simplify often. All right, let's take a look at a few more examples, just practicing. All right, don't really have any simplifying I can do here, but we're taking the derivative of 7 to the u. So the derivative of 7 to the u would be 7 to the u times the natural log of 7, there's your constant, times, now I got to take the derivative of negative 3 over x. All right, so let's think about the derivative. I would probably rewrite that as negative 3x to the negative 1, so I don't have to use quotient rule. So the derivative of that final inside function is going to be 3x to the negative 2. And now we're done. All right, so the derivative of the log with the constant, because that's the derivative of the, derivative of the exponential with its constant, and then derivative of the u. All right. Now here, don't go straight there. Don't take that derivative and use chain rule. E to the ln of x is nothing more than x, and its derivative is 1. So there's really no thinking to that one. All right, here we're going to have to use the substitution. We're going to let u equal this whole thing in here, so it's u squared. The derivative of u squared would be 2u to the first times, chain rule, derivative of the u. Now, derivative of the u, the derivative of the sum is the sum of the derivatives. The derivative of e to the negative t is itself a chain rule. It's e to the negative t times the derivative of negative t, which is negative 1, plus derivative of e to the t, which is e to the t. If we want to, we could pretty it up a little bit. This is 2e to the negative t plus e to the t times negative e to the negative t plus e to the t. Don't forget that e to the negative t requires a chain rule. That's the most commonly missed question because of just carelessness, that you forget you have to use chain rule there. All right, here I'm going to have a product rule, and then I'm going to have a chain rule. I'm going to do this in steps. I'm going to consider this to be the first function, that to be the second function. So the derivative of a product would be the first times the derivative of the second, I'll leave a big parenthesis there, plus the second times the derivative of the first, 2x. So I've left that really difficult one to do, so I'll kind of do a little work here for this one. This is chain rule within chain rule within chain rule, so let's think about it. Again, we could start doing the u's and the substitutions and the v's and the w's, but I'm going to try to do it without that. So I have 5 to the u. The derivative of 5 to the u would be 5 to the u times derivative of exponential 5, I need my log of 5 in there, times, now I need the derivative of sine squared of 4x. Alright, now the derivative of, this is now v squared, so it would be 2. But yeah, maybe let's back this one up and let's do this all the way with some letters, because I don't think y'all can do that in your head. Let's go all the way back. I'll fill this in a second. We'll come down here. I need the derivative. Let's just go derivative of 5 to the sine squared of 4x with respect to x. That's what we're going to fill in there. Alright, let's show the work for that, just so that y'all don't mess it up. Alright, so we have u equal to sine of 4x, and I'm going to write it squared. So I need to find du dx. Now to find du dx, I really am thinking of this with a v. V is going to be sine of 4x. I'm working my way in. Right? So I want to do dv dx. And so when I look at this, the derivative of sine is cosine of that times the derivative of the inside times 4. So I keep going until I get myself down to something I can do the derivative of. Oh, see, and I totally just made a mistake there. See, I'm getting tired. I'm done. It's 6 o'clock at night, and I really want to be done with this video so that I can go home. So let's start that again. So v would equal sine of 4x. No, actually I was good. I was thinking I was wrong. Derivative of sine is cosine 4x, and then that whole thing times 4. Now, this is v squared. The derivative of v squared would be 2v times, now I need to do this dv dx, cosine of 4x times the 4. Alright, and now I got to work myself back to this, so let's come back into our little string here. I'll write it below. We had x squared times, now in order to do the derivative, we have to do the derivative of 5 to the u, which is 5 to the u times ln of 5 times du dx, which is 2 sine of 4x, I like parentheses, times cosine of 4x times that 4. And then finish out our 5 sine squared of 4x times 2x. So this is our derivative. Very complicated looking. And if I needed to simplify that, I mean, like heaven help us, but all it is 2 terms, and you would look for common factors. They both have a sine, 5 to this power, and I have a 2 and an x that I could pull out. I'm not going to do that, but you could if you needed to work on it. Alright, let's look at this one. Do not be tempted when you're doing this problem to think that you're doing product rule here. This is a constant. Got to get you guys to recognize when you have to use a rule and when not. So it's a constant times x, and so don't get tricked in that one. The derivative is e cubed. It is not a exponential function that you are doing the derivative of. Alright, example 17. Actually, you know what? I think that I am going to stop there because I've done enough of doing this for you. I'm going to let you work on this in class next time. So to finish out the last of this worksheet, instead of me doing it, I'm going to let you do it because I don't really have any worksheets for this, and this will be kind of like your worksheet practicing this.